Okay, next up, rotational force. I'm going to propose an expression for calculating rotational force and then justify it, prove it, but sort of derive it in a way. And then the next step is to sort of evaluate it. What does it mean? What does it do for us? So far, we have talked about rotational mass, moment of inertia, and rotational acceleration, alpha. Now I'm thinking about NA, right? If I add up the linear force on an object, I get the mass times the acceleration. If I add up the rotational force as opposed to the linear force, if I add all that up, I expect to get the rotational mass times the rotational acceleration. That's how I really want it to go if things line up like they've been lining up so far. Okay, let's see how this works. To keep things nice, I'm going to rotate an object, a single object, a mass m, in a horizontal circle in the x. Well, all right, well, I'll draw it this way first. In this case, it's the xz plane with the y-axis going through the middle of it. So imagine there is a single object m, maybe at the end of a string, spinning in a circle of radius r. A horizontal circle of radius r. There's only one mass to worry about. So when we calculate the moment of inertia of this situation, there's only one term to add, and we can do it discrete. We don't have to integrate because it's just a particle, just a point. Its mass times its square distance from the axis of rotation. That's what we've got, mr squared. Okay, cool. So we're going to rotate with some angular velocity omega. This way. And I want to speed up. Yeah, I want to put a little rocket on that mass and give it additional thrust so that it moves in a faster circle. Okay. So in order for this to be convincing, I basically want to start with what I know to be true, Newton's second law, and modify this until it looks like that. The tangential acceleration that would cause us to speed up, well, the actual acceleration that would cause us to speed up, is the angular acceleration cross the radius vector. And now, for no particular reason, but I mean, I guess there is some, well, obviously there's a particular reason, but I see MR. And I think about moment of inertia, and if I had another R, then I'd be talking about MR squared, and then I'm pretty close to that as long as the vector nonsense straightens out. So I'm going to multiply by vector R, but in order to multiply, I need to decide whether I'm cross or dot product. I don't want to lose the vectorness because I want to have vector angular acceleration still left over when I'm done. So I'm going to take the cross product of vector R with both sides of the equation multiplying from the left. Because again, the cross product is anti-commutative. It matters the order in which we write the multiplication. Cross M alpha cross R. Now, the multiplication by m, that's scalar. If we scale this result and then do some cross product, or if first we do the cross product of r and this, and then scale by m, that's the same. Regular multiplication by scalar is, commutative, associative, all the stuff. So we can, move that out here. And we're talking about R cross alpha cross R. Now, there is an identity from vector multiplication, the triple cross product, that I'm going to look up for right now because I never remember what the identity is. It is something that we can look up, and in fact, you know what? I'm gonna create a tab here, and then I'm gonna share my screen with you so you can see this, see what I'm doing. There we go. Okay, so I'm gonna Google vector triple product. Scalar triple product, no. Vector triple product, here we go. Triple product expansion, or Lagrange's formula, is this thing. And we're going to use that here. So I'll leave it up on the screen. I'll write what it says, and then I'll stop sharing so you can see the whiteboard. Equals M. Okay, so we want the dot product of A and C, which are the outside ones. So that's R dot R times the middle one, so it's alpha, minus the dot product of the first two, R dot alpha times the third R. Okay, so I've expanded the vector triple product using Lagrange's formula, and we've ended up with that, which is obviously better. Is better for reasons that we're about to find out. Alpha is the angular rate of change of velocity. It's the rate of change of angular velocity. Angular velocity is in a direction. Let's see, we're rotating this way, so omega points in the positive y direction as drawn. So does alpha. R, the radius vector, is in the xz plane, perpendicular to the positive y direction, the direction of alpha. R and alpha are perpendicular, so that dot product is 0. That whole term goes away. R dot R, that's R squared. And that's what we wanted. MR squared alpha. Apparently, what we need for a definition of rotational force, R cross net force. So, okay, so we take all the forces, we add them all up like vectors and then cross with R. Or I suppose we could add up all of the possible things, R cross F. Which means rotational force is R cross F. The way I remember which comes first, R or the other thing, is whether we're trying to get to linear or to rotational. Here, we're trying to get from rotational to linear. The vector on the other side of the equals is linear. So it's rotational cross R. If we're trying to get to rotational, then it's R cross linear. That's how I remember which comes first, because it matters. The cross product is anti-commutative. It matters whether we write R cross F or F cross R, and I don't want to write F cross R because it should be this. Rotational force is, I'm going to call that torque, never to be confused with twerk. You do not want me to talk about or demonstrate the second thing, nor will I. Torque, however, we will talk about. The symbol that I like to use for that is the Greek letter tau. It's like a backwards capital J. It is vector, R cross F, because the cross product gets us a vector result. Again, that's Greek letter tau, T-A-U. And we can modify this so we can talk about the net torque. The sum of all the torques is the sum of all the individual torques, R cross F. Or it's the cross product of R and the net force. Using that definition, we can fix this. This is the thing that is equal to this, which is what we wanted. So net torque, sigma tau vector, is equal to I alpha, and this is our rotational version of Newton's second law, because this is where we started from to get to it. Excellent. I'll stop the segment there. And we'll pick up there in the next one.